Let's look at drag forces, and I guess that's the general name for the unit. It doesn't have to just include air resistance, but so drag force is typically going to be a resistive force that's in the opposite direction of velocity. The easiest case is just to take a ball and just to drop it above the ground, okay? And we'll drop it, so we'll say the initial velocity is equal to 0. And let's take a look at it. While looking at it, we want to look at a force perspective. And so we have gravity pulling down, and then we have this drag force opposing the motion. And as long as we're dropping the ball, the velocity is going to be down, and then the drag force is then up. More specifically, we're going to model the drag force. And there's two ways to look at it. The first way is that it is opposite the velocity, so that's the negative sign, and it's proportional to the velocity. So as the velocity grows, it's linearly proportional to the velocity. As the velocity grows, so does the drag force, and then this B would be the drag coefficient. All right, that's some drag coefficient. This allows dropping a pen and dropping a ball and dropping a quarter, all are going to have different B values, but roughly their drag is still going to be in the opposite direction, somehow proportional to the velocity, so the drag force grows. So when we write this out in F equals ma, we end up getting a differential equation. The drag force is going to be, and we know the acceleration is going to be down, so we'll treat down as positive. Mg minus bv equals m, and instead of a, we're going to write dv dt. And we get a differential equation. We get a differential equation because we have an equation that relates the velocity to the derivative of the velocity, and that's kind of the definition of a differential equation. I'm going to use separation of variables just like in AB Calc, and the variables here are velocity and time, because the goal is to take this differential equation and get an equation for the velocity as a function of time. That's the end goal here. And so it's like we're solving for y in terms of x, except in this case we're solving for v in terms of t. I'm going to take this m and I'm going to move it over here along with the dt. I'm going to divide by that whole thing, dv over mg minus bv. I have successfully separated the variables. The t's, in this case there is no t yet, I'll get one when I integrate, are on the left side, and the dv and the v's are on the other side. If you integrate both sides, so if that's a true statement, so is this. When I integrate 1 over m is just some constant, and I get 1 over m times t plus some initial value c. And then over here I have to be careful. I'm going to get a negative 1 over b natural log of mg minus bv. So that's me doing a little u substitution and realizing that it's a logarithm. So essentially it's a du over a u. And we know from calculus that the integral of du over u is the natural log of u. Okay? The negative comes from this negative sign, and the 1 over b comes from the reverse chain rule, or if you went ahead and actually went through the u substitution, you'd get this value. Now let's use the initial value that we know that at t equals 0, v equals 0. So when we plug those in, we get 0 plus c equals negative 1 over b natural log of mg, right? That goes away and that goes away when we use those values, and it gives us the ability to solve for c. So now we know c. So I'm going to come up here now, 1 over mt plus c, so minus 1 over b natural log of mg equals negative over 1 over b natural log of mg minus bv. I am really done with the physics. I was actually done with the physics right here. This is physics, the rest of this is separation of variables and integration using calculus. I'm going to multiply everything by negative b, so it's going to be negative b over mt, and then I just get a plus natural log of mg, and then over here I just get the natural log of mg minus bv. And then I'm going to exponentiate, which means if those two things are equal, e to them also has to be the same thing. E to this plus this, you look back in your algebra rules, is the same thing as this. Right? E to the natural log of mg is just an mg out in front. And over here they delete each other, right? That exponential and the logarithm are inverses. I'm going to add the BV over here and subtract that. And so I get BV equals mg minus mg e to the negative b over mt. And then I'm going to do two steps here. I'm going to factor an mg out, and I'm going to divide by b, and I get my goal. V equals mg over b times the quantity 1 minus e to the negative b over mt. And now we have our goal. We have the velocity as a function of time, meaning I can tell you exactly how fast it's going after 1 second, 2 seconds, 3 seconds. Now remember, old school, we used to be able to say that the velocity was just some v naught, minus gt in free fall. Well, that's because the only force acting on us was gravity, and so we knew that we would fall at 9.8 meters per second every second. Well, that changes because now we have some drag force. We're not actually falling at g the whole time. Our velocity is going to be a little more complicated. Let's take a look at what this looks like from a graphical perspective. Hopefully this will make sense. That at t equals 0, we start out at 0. And this equation we might not know much, but this is a 1 minus an exponential, and it's going to go like this. And it's going to asymptotically approach some value. So think about what happens here. Look at the limit of this as t goes to infinity. If you plug infinity in for time, e to the negative infinity is just 0, and so then this term goes away, and you're left with the velocity as just mg over b. So not only do we know that it approaches some value, we know exactly what that value is. That value is mg over b, and we have a name for that. We call that the terminal velocity. That's the velocity that the object will approach if you let it in the air for 10 seconds, 20 seconds, whatever. It would depend on what b is, how long it takes to truly reach something. I mean, technically it takes an infinite amount of time for this to go to 0, but realistically, terminal velocity is probably, a 10-second type thing. Drop it from a really tall building, it's going to reach terminal velocity, or drop it from an airplane, it's certainly going to reach terminal velocity. Those two speeds probably would be, within 1% of each other at the impact. But this curve hopefully makes sense. Look at the slope here. The slope is the acceleration. Where's the slope the greatest? Right at the beginning, what should the slope be? Well, at the very beginning, there's no drag force. And so the only force is mg, and so then the acceleration is just g. And so this slope should be like 9.8. But then as soon as you start getting a velocity, the drag force bv starts growing, which makes the overall force down smaller, which makes the acceleration smaller, and it keeps tailing off and tailing off and tailing off, and then eventually there's no more acceleration. Because eventually, what happens? Well, take a look at this equation. Eventually, the acceleration goes to 0. Well, when the acceleration is 0, what is this? That just says that those two things are equal. And look how easy that was. I found the terminal velocity in 5 seconds. And I guess a nice teaching point is, you don't need to do any of this differential equation stuff to find the terminal velocity. You can just force the acceleration is equal to 0 and find that specific velocity. Again, we can't do this to find the velocity as a function of time, but if we just want to know the terminal velocity, make the acceleration 0 and find the velocity such that this is a true statement. Well, this is a true statement when these two are equal, and so the terminal velocity is just mg over b, which does satisfy the same thing we say over here. That coefficient out front is the terminal velocity, meaning it's the biggest that function ever gets. And it does happen at t equals infinity, or probably even 10, 20 seconds in the real world. So that's the easiest version of drag force. I'll look at some future situations on a different video.